Good evening, everyone. Today we'll be talking about a project presentation for the subject pattern recognition. For my project, I'm doing it on fingerprint recognition using minutia matching. Let me just get the slide started. So the topic is fingerprint recognition using minutia matching. Now, traditionally, we have seen all the traditional authentication systems. It was mostly based on IDs and passwords, and now this particular technique had two certain advantages. One, it was simple to remember for the user, and it was easy to integrate in different identification systems. But nowadays, we have a large number of users who are connected online, and there's a lot of data that is being secured everywhere. And it is now imperative that we design something which is centered around the user themselves, something which could be tracked to one particular user and not as a general system. So for this, we moved on to experimentation with human biometrics, and we have been able to design systems around human biometrics to ensure that the services are actually accessed by a legitimate user and there is no fraud or any other discrepancies involved. Now, you might be thinking, what is biometrics? Like, what are biometrics? Now, if you look at your own body, you'll see we all have unique personal attributes. Now, biometrics are basically an individual physiological characteristic. It could be anything from the shape of your fingers to your eyes to anything that stands out. So, for us, for human beings, we have observed that the fingerprint of the if you have your finger, you'll see there's like lots of patterns and edges and different ridges on your finger. The print that we could find out of those ridges is actually unique for every human being. And similarly, the retinal scans or the voice, these are all certain attributes that is common. But the one best thing about fingerprint is it is absolutely unique, and there is no other human being with the same fingerprint. So it makes a very good biometric to work on. Now, you might be thinking, okay, but if I have my cards, it like and all, like why do I still need to have anything regarding biometrics? Well, the thing is, our ID cards could be stolen, and any good password, no matter how good it is, it still can be cracked with some effort. Nowadays, we have supercomputers. We have computers that can compute at terabyte petaflops, but we need something which would be stand out, which would not be cracked. This is why we are building identification systems based on individual attributes, because it would provide more reliability and it would provide more security. And your passwords, since there would be no password, it'll just be your own biological attribute, your own biometric that can never be cracked, because no two human beings will have the same biometric to begin with. That's why we say, like, your face can't be stolen, but your password can be. Now, fingerprints as biometrics, I have been talking about in my two slides back that it is the best one. Over here, we have different types of biometrics that we have here. One is facial recognition, one is iris recognition, which is basically the retinal scan. One is fingerprint recognition, one is voice recognition. Now, as I was talking, recognition is the most widely used biometric. Every human being has a unique fingerprint. No two fingerprints are the same. And the best part of fingerprint recognition is it's absolutely simple to implement, and it could be combined with all different types of biometrics for an even more secure system. Now, let's move on to the system level design for our project. Like, I have designed a fingerprint recognition system using minutia matching. So we have three blocks which are mostly essential. One is the input sensor, one is the minutia extractor, and another is the minutia matcher. Now, input sensor basically takes in the fingerprint, it scans the human fingerprint. The minutia extractor is the one which does all the necessary steps of enhancing the image, to converting it to binary standards, extracting the different ridges and the minutia points, marking them, removing any false minutia, that may be present in the fingerprint. And a minutia matcher just simply takes the input fingerprint and matches it with the database to find out who it belonged to. Or else, for example, if you have like two different fingerprints, we could just take two different fingerprints, pass them to the minutia extractor, and then we pass it to the minutia matcher, where basically both of them will be checked whether they have the same characteristics or not. So that's what minutia matcher does. So the end result will be either be a fingerprint match or fingerprint no match. Now, let's talk a little more about the input sensors. The input images that we obtain can be directly obtained from any optical sensor or a semiconductor sensor. So now the input images that I have been using for my project have variable noise and clarity levels so that I could account for all different image conditions, because it may be possible a user's hand may be dirty or it may be a slightly scarred. Still, like, how you would actually get the good fingerprint out of those hands, that is the trick. So I want to involve all different conditions of an image so that the system that I develop would be absolutely very versatile and it would be absolutely accurate in getting the fingerprints. So that's what, like, we like mostly it's all been taken through like ink mapping or directly from the sensors. There's a lot of different images that have been taken into account and analyzed. Next, we move on to the first block of the minutia extractor. It's the pre-processing block. Now, the pre-processing block has certain substages. First, it's the image enhancement. Now, from the word enhancement, we can realize that it's about improving the quality of the image. It improves the obtained input images. It's about increasing the contrast and improving the basic clarity of the fingerprint images. There are two techniques we involve over here. One is histogram equalization and one is fast Fourier transform. Now, histogram equalization basically helps us to expand the pixel value distribution of the fingerprint image so that we could increase the overall perceptual information from the image. The image could be more, it could give us more data from the image. And you could see like the two diagrams which show us, on the left side we have the original image compared to the image that is enhanced by histogram equalization, and the respective graphs also for regarding that. So you can see the one on the histogram equalization is much clearer and it's more with the clarity. Now we use, other than histogram equalization, I'm also using fast Fourier transform so that like we could get the most clarity out of the image, like it would be a very good clear image. So the fast Fourier transform basically divides the image into small processing blocks of 32 by 32 pixels, and we use the given formula over here to calculate like the respective ranges. Now what we follow the process is that we calculate the FFT of each individual block and we multiply it by its own magnitude so that each and every block is enhanced by its own dominant frequency and no other external frequency. So you can see we still obtain a very good high image from the FFTs. So there's like on the left we have enhancement by FFT and on the right we have enhancement by histogram equalization. So both of the images are there and we get like, and you can see to the image on the left that you could actually understand the blocks of 32 by 32 pixels. So these give us more clarity to the image. So this will help in overall system accuracy. Now let's talk about the second substage, is the image binarization. So what image binarization does is it divides the blocks into blocks of 16 by 16. Now what we do is we calculate the mean intensity of each block and we compare it to the intensity of each individual pixel present in the block. Now if the intensity of the pixel is higher, then we denote it as a object pixel, and if it's lower, it's a background pixel. So for image binarization, it's used to convert it into binary format by dividing it from 16 by 16 and then finding out an object pixel and a background pixel. Next, the image segmentation stage is very important. It analyzes the data obtained from the image binarization. It confirms whether the region that image binarization stage told us as an object or as a background. So after confirming, if it's found that this particular region is background, it basically removes it from the image. Now for doing this also, it's very tricky to absolutely be certain which region is background. We use two techniques over here. One is block direction estimation, one is morphological operations. Now for block direction estimation, we basically use two Sobel filters, and we calculate the gradient values of each of the direction for each block. Then we calculate the number of ridges present in the block and the certainty value, so that we could determine if a block is a background block or not. And the respective formulas are shown with the picture, which just shows the orientation and the flow estimate, like which side actually the image could be in, like the ridges or the patterns, like which side is the direction of the block, which is the direction. Now morphological operation is done above on top of the block direction, so that we could be absolutely certain in eliminating any unwanted regions. Now we have like two different operations that we do. One is open and close. Open is done to expand the image and remove any unwanted peaks, whereas close, it shrinks the image and removes any small cavities. So both these techniques are, first we do open so that we have all the unwanted peaks gone. Next we do close so that we have all the cavities gone. This brings us to a complete whole structure. Now next we talk about the minutia extraction process. Now for the minutia extraction, like there are two certain things. One is ridge thinning. Now first, we knew in image binarization we had it as 16 by 16 for the image segmentation, and binarization, like for FFT we had it at 32 by 32 pixels. Binarization changed it to 16 by 16. But what ridge thinning does, it divides it into blocks of 3 by 3 pixels, so that we can scan and remove any ridge which is more than a pixel wide. After that, morphological operations is also performed to remove any type of edge breaks, that we call them, or isolated points or any single point ridges. This is done so that we could get more clarity out of the image, and like it may be free of any errors that may be present. Next we'll be talking about minutia marking and detection, but we'll talk that on our next video.